Good morning, all of you. Welcome to Sri Jayendra Rank Zone. So, in the first lecture, we have completed about in chemical kinetics. We have completed rate of reaction as well as how to write rate expression for a given reaction. Now, in this lecture, we are going to do new topic. So, it's very important. Let us start the new topic here. Yes, it's coming now. So, in the first topic, what we have done so far, we have done completely first lecture. What is rate of reaction and also factors affecting rate of reaction, how to express rate law for a given chemical reaction, etc. And we have done some numericals also. Now we are going to continue the topic in chemical kinetics. Apart from that, also we have seen how to find out order of reaction. Now what is there in this session we'll discuss now. So first, next topic we have fractional order reactions. Fractional order reactions. Let us start now. This is fractional order reactions. What is fractional order reactions? As we already know, the order of reactions can be negative zero also, and even it can be a whole number. And we have seen examples in the previous class, the whole reactions which is based on whole number zero order also. So zero order reactions, first order reactions, second order reactions. So now, next we are going to discuss fractional order reactions. What is fractional order reactions? Yes, please wait. Yes, fractional order reactions. These are the reactions in which the sum of the exponents of the concentration terms in the rate equation is a fraction. The sum of the exponents, the sum of the exponents, yes, the sum of the exponents, the sum of the exponents of the concentration terms in the rate equation is a fraction. Let us discuss now. So examples of fractional order reaction. Fractional order reaction. So let us see first example. Hydrogen combines with the bromine to form two molecules of hydrogen bromide. So the rate, let us say for example, the rate for this expression is K, R is equal to K into concentration of hydrogen into concentration of Br2 whole to the power 1 by 2. So this is just experimental data only. And the overall order of the reaction is 1 plus 1 by 2, because order is equal to sum of the stoichiometric powers of the reactant. Sum of the stoichiometric powers of the concentration of reactants is called order. Sum of the stoichiometric powers of the concentration of reactants is called order. So order is equal to 1 plus 1 by 2, it is equal to 3 by 2. Let us take one more example. Acetaldehyde, this is called what? Acetaldehyde, CH3CHO, on heating forms CH4 and CO. And the rate for this reaction is given as K into concentration of acetaldehyde whole to the power of 3 by 2. So order is equal to, straight away we can write order is equal to 3 by 2. So these are nothing but examples of fractional order reactions. Let us take one more example. So this is C2H4, that is ethene plus iodine forms ethene iodide, which on for this rate is equal to K into ethene into iodine, concentration of iodine whole to the power of 3 by 2. So order is equal to 1 plus 3 by 2, which is equal to 5 by 2. So in this way, we'll find out examples for fractional order reaction. And last example, methyl chloride, CHCl3, chloroform, on reaction with chlorine forms CCl4 and HCl. For this, the rate is given as K into CHCl3 into concentration of Cl to whole to the power 1 by 2. So it is equal to 3 by 2. So by this, what you can understand, so order of reactions can also be fractional, and order of reaction does not depend on, one more writing I'm writing here, order of reaction does not depend on does not depend on does not depend on chemical equation does not depend on chemical equation depends on chemical equation only by experimental. It is based on experimental data. It's based on experimental data. So the order of reaction always is an experimental data. So order of reaction is experimental data. I hope it is clear. Next we have pseudo first order reactions. What is this called? Pseudo first order reactions. The order of reaction may be altered sometimes by changing the conditions. For example, by taking one or more reactants in excess compared to the others. So that is called. So for example, consider the acid hydrolysis of an ester. Ester means CH3COC2H5. Acid hydrolysis means in the presence of acid. For the ester, if you add water, so in aqueous solution, it forms acid as well as ethyl alcohol. So it is acetic acid as well as ethyl alcohol. So this is the equation. The rate expression for this equation is actually you have tried concentration of ester into concentration of water. But if you notice this by the experimental data, you notice that however water is present in large excess in the reaction mixture and its concentration of water may be assumed to be constant during the course of reaction. So the rate law therefore becomes it doesn't depend on water, it depends only on ester. So since water, even if you add water also, there is no change in the rate of reaction. So what is the meaning of this is nothing but even even with excess of water also, with excess of water, there is no change in rate. There is no change in rate takes place. So due to which what happens, the rate of reaction is depending only on concentration of ester. So where K of H2O is a constant. Thus the reaction reduces to first order, even though it contains two molecules, but it is first order. Such reactions are called as pseudo first order reactions. So this is called pseudo first order reactions. I hope it is clear. So what are pseudo first order reactions? In a chemical reaction, if by the addition of the one of the reactant, as there is no change in the course of the reaction, by the addition of even one of the reactant like water present in excess, large excess also, the reaction mixture, in the reaction mixture, there is no change in the course of the reaction. Due to this, what happens? It is independent. So rate for this reaction is independent of concentration of water. So that is why it is called as pseudo first order reactions. This is called these reactions are called what? Pseudo first order reactions. So this is very important. So pseudo first order reactions. Example: esterification of hydrolysis of ester. So hydrolysis of ester gives acid plus alcohol. So and ester rate is proportional to only concentration of ester, not with water. So this is called pseudo first order reactions. Pseudo first order reactions. Next, so pseudo first order reactions are the chemical reactions in which the molecularity is more than one. As I told you, molecularity here, two molecules are involved. So molecularity is more than one, but follows only first order kinetics because it is depending purely on the only one quantity of the reactant, not the two quantities of the reactants. So rate is equal to K into, for this example, sucrose, concentration of sucrose. Sucrose on reaction with water form glucose and fructose is already we know. So for this reaction, it is observed experimentally that rate is proportional to only concentration of sucrose, not with the concentration of water. Since the concentration of water, how much water is added, also there is no change in the rate of the reaction. So that's why rate is proportional to only concentration of sucrose. So due to which what happens, this reaction is also called as pseudo first order reaction. Next. Units of rate constant. The units depend on the order of reaction. The units depend on the order of reaction. From the rate law, we can say rate is equal to K into A to the power of P, B to the power of Q, C to the power of R, that is concentrations, where K is equal to this much. And the units of K becomes, since you know concentration becomes moles per liter per second. So by adding this, we'll get order of the reaction. So for any order of the reaction, for any order of the reaction, moles per liter, 1 minus n, second inverse, where is the order of the reaction? The n is called the order of reaction. What is the n? N is called order of reaction. Here we should write here it as, n, where n is called order of reaction. This n is called order of reaction. So simple, we can write it as mole to the power 1 minus n, liter to the power n minus 1, second inverse. Mole to the power of 1 minus n, liter to the power of n minus 1, second inverse. For example, first order reaction, we can write 1 minus 1, n 1 minus 1. So second inverse is the answer. So let us see what is the units. We'll see now. I'll explain it clearly now. Next, the units of rate constant of reactions of different orders are given below. For zero order, it is moles per liter per second, or moles per decimeter cube per second inverse, or moles per second inverse. So by seeing the quantity of K, by seeing the unit of K also, we can say the order of reaction. This is one more method to find the order of reaction. So by seeing the unit of K, we can find order of reaction. So here zero order. Zero order means, for zero order, what is the unit? Moles per liter. Mole to the power of 1 minus 0. 1 minus 0 is 1. So even you can see this original formula I'm writing here for any order of reaction. Moles per liter whole to the power of 1 minus n, second inverse. This is common for all. So for example, 0 means n value is 0. So it becomes moles per liter. 1 minus 0 means 1. So moles per liter whole to the power of 1. That is 1 minus 0 for your understanding. Second inverse. 1 minus 0 is what? 1. So moles per liter, second inverse. Moles per liter, second inverse. Moles per decimeter cube or molarity per second. This is called molarity per second. Next, first order. First order, apply the same formula for this. First order. So we can say moles per liter whole to the power of 1 minus 1. Because 1 minus n means here 1, first order, into second inverse. So 1 minus 1 is 0, anything power 0 is 1. So simply the order unit of first order reaction is unit of K for first order reaction. The unit of rate constant for first order reaction is second inverse. Similarly for second order, moles per liter, liter second inverse, or moles per liter decimeter cube second inverse, or molarity inverse second inverse. And third order reaction, similarly, moles per liter, moles per minus 2 liter square second inverse, or moles per minus 2 decimeter 6 second inverse, or m minus 2 s minus 1. I hope it is clear. So this table is very, very important for competitive exams. So this table is very, very important. You have to refer this table. And the general form for writing equation is how much? Mole per liter whole to the power of 1 minus n, second inverse, for any order of the reaction, 0, first order, second order, anything. So in place of n, we have to write the order of reaction. That's all. So by seeing the units of K also, we can find whether it is first order or second order or zero order reaction. So it is another way of finding K, rate of reaction. Next, example 1. Identify the reaction order from the rate constants. K is equal to 2.3 10 to the power of minus 5 liter mole inverse second inverse. So let us check now which order it becomes. So moles per liter whole to the power of 1 minus n, second inverse. This is a general order. So let us take in here first order is second inverse. Second order will try. So moles per liter 1 minus 2, second inverse. So 1 minus 2 becomes minus 1. Minus minus becomes plus. So mole inverse liter second inverse. So mole inverse liter. I'm writing it again. inverse liter, because minus 1 minus becomes 1, liter plus 1, that is second inverse. So mole inverse, liter, second inverse. So answer is second order. So this is the answer is second order. Second order. Let us see now. 100% this will be second order only. So I hope it is clear. So this is the question number 1 examples. Next concept. Order of reaction from initial rate method. Very, very important. Order of reaction from initial rate method. So if the concentration of the reactant is made m times, keeping the concentration of other reactants constant. So if the concentration of reactant is made m times means m times it is multiplied, keeping the concentration of other reactants constant, then the rate of reaction becomes m power n times, where n is the order of with respect to the reactant. So this is called R2 by R1 is equal to C2 by C1 whole to the power of n, m to the power of n. This formula is very, very important. So since if you change the concentration of the reactant, automatically the rate of the reactant also, the rate of reaction also changes by keeping others constant. For example, consider two reactants. So for example, consider two reactants, concentration of A, two reactants, concentration of A and concentration of B, for example. So by keeping B constant, if you increase the concentration of A for 5 times, then rate of reaction changes also. R2 by R1 is equal to C2 by C1, that is initial concentration by final concentration, whole to the power of n, that is 5 times. That is equal to m to the power of n. So like that you get. So this is called what? So for example, if the rates R1 and R2 at concentration C1 and C2 of a reactant are measured experimentally, the order with respect to that reactant can be determined easily. So by using the rate, we can say the order of the reaction easily. That already we know. With that particular reactant means now we are going to split the reaction. Next. Now, for example, if you see here, for the reaction A plus B gives rise to products. For the reaction A plus B gives rise to products. The rate law expression is taken as rate is equal to K into A to the power of 1 by 3 into B to the power of 2. What is the order of reaction? Order of reaction simply by adding these two. So easily we can try. So order of reaction is, or what is order of reaction? Sum of the stoichiometric powers of the rate expression. So that is 1 by 3 plus 2, which is equal to 7 by 3. So this is called order of the reaction. Next, second question, what are the units of rate concentration of is measured in moles per decimeter cube, moles per liter, and time in seconds. So what is the order of this reaction? So which reaction, what are the units of rate constant, K values? So straight away we can take K value. Units of rate constant K is equal to, how to find out rate by, K is equal to rate by, K is equal to rate by concentration of A to the power 1 by 3 into concentration of B to the power 2. So you can find out the unit. So what is the concentration, rate concentration? So rate, it is nothing but, so if the concentration is measured in moles per decimeter cube, so concentration is measured in moles per decimeter cube means moles per decimeter cube, whole to the power 1 by 3 into moles per decimeter cube whole to the power of 2, like that you get. So if you substitute the formula, automatically you'll get the answer. So I hope the answer will be dm4m moles minus 4 by 3 second inverse. Just in place of m, n you have to write 1 by 3. So straight away you'll get the answer. So first one is 7 by 3, second one is dm4 mole per minus 4 s to the power of minus 1. Next, third example. For the reaction 2A plus B gives rise to A to B. The rate law is R is equal to K into concentration of A, B to the power of 2. Where K is equal to this much value is given, that is 2 into 10 to the power of minus 6 moles minus 2, mole inverse minus 2, liter square second inverse. Calculate the initial rate when A is equal to 0.1, B is equal to 0.2. Calculate the rate of reaction after A is reduced to 0.06 molarity. Very big numerical. Straight away they are asking calculate the initial rate of the reaction when A becomes 0.1 and B becomes 0.2. K is given. So initial rate, this is the rate expression is already given. Straight away applying the formula. So R is equal to, just I'm trying to solve this numerical, you can just see R is equal to, for this equation, K into K value is given 2 into 10 to the power of minus 6, because the rate expression is this, is the rate expression, applying this only, into concentration of A. Concentration of A is given how much? 0.1 into concentration of, and the A is to the power 1, so power 1, into concentration of B. Concentration of B is given how much? 0.2. 0.2 whole square. So substituting this, 2 into 10 to the power of minus 6 in 0.1 is 0.2. 2 into 0.1 into 0.2 into 10 to the power of minus 6. So after calculating, you'll get the answer. So this is the formula for finding R, because they have given R is equal to K into concentration of A into concentration of B whole to the power of 2. Next, what is the second question? Also calculate the rate of reaction after A is reduced to 0.06. So when they ask for A is reduced, K value doesn't change for the same reaction. So this is first case R. Second case R, how to find? R is equal to K value is 2 into 10 to the power of minus 6. Is taken as common. A value, concentration of A value becomes 0.1 minus 0.06, because reduced up to 0.06, reduced to 0.06, and the concentration of B becomes 0.2 whole square as it is. Now you multiply these three things, you get the answer. I hope it is clear. So clearly you can understand they are asking us to calculate the initial rate of the reaction. Initial rate of the reaction. Rate of the reaction is given by the formula from this equation. R is equal to K into concentration of A into concentration of B whole to the power of 2. This is experimental data. So this one you have to see. We should not see the skeletal equation. We have to see only the rate expression and substituting the values. They have given value of K, value of concentration of A and concentration of B. Straight away substituting the values, you'll get the answer. So similarly here also you'll get. I hope it is clear. Now we will check the answers. After multiplying, you'll get the answer as, so first one in the case 8 into 10 to the power of minus 9, because 2 into 0.1 is 0.2 becomes 0.008. I'll write it here again. Since 2 into 10 to the power of minus 6 into 0.1 into 0.2 becomes 0.008. That is 8 in 10 to the power of minus 3 in 10 to the power of minus 6. This becomes 8 into 10 to the power of minus 6 into minus 3 becomes 8 into 10 to the power. First, second one also you'll get the same. So second one also you'll get like this, 3.89 10 to the power of minus 9 moles per liter per second. So in this way you have to calculate. I hope this sum is clear. This model is very, very important for all objective exams. Next question. Very, very important. The rate law for a reaction is found to be rate is equal to K into concentration of NO2 minus into iodine minus into concentration of iodine minus into concentration of H plus whole square. Very, very important. So this is the actual rate of the reaction. Forget about the reaction, how it could be. Only we have to see the experimental reaction. How would the rate of reaction changes when keeping all other constants, only concentration of H plus is doubled. So you can see from rate, concentration of H plus is to the power 2. So if H plus is doubled, rate increases how many times? 4 times. So answer is, because they are in the ratio of 1:2. So if H plus is doubled, rate becomes how many times? So rate of reaction would change when concentration of H plus is doubled, becomes 4 times, because it is, since R is proportional to concentration of H plus whole to the power of 2. If it is 1, only 2. But it is 2, so that's why it is total 4 times. Next, concentration of iodine minus is halved. So iodine minus, if we decrease to half, automatically, since rate is proportional to concentration of iodine minus, so rate is also halved. So second one is halved. Third one, concentration of all the reactant is tripled. Tripled means 3 times. So by this we can write rate is proportional to K into concentration of NO2 minus into concentration of I minus into concentration of H plus 2, H plus whole square. On the whole, it is tripled means here we'll get it is 3 times 3 into 3 into 9, because 2 times already, so 3 times means 3 is a 9. So it becomes 81 times. What is the answer now? 81 times. So if all the concentration of the reactants are tripled, so the rate of reaction increases by 81 times. I hope it is clear. Now let us check the answers. So first time it is 4 times, right? Second time it is half. Third time it is 81 times. So 81 times. So it is clear. Very, very important model. Like these questions you may expect in the competitive exams. Next. This model is also very important. They'll give you a tabular form and they ask us to find rate law expression for the given table. So rate law expression, not by seeing the equation. We have to see by experimental data. This is called experimental data. So let us solve this question. So if you carefully observe this table clearly, it has nitric oxide, oxygen gas, and formation of NO2. This is rate of formation of NO2. That is moles per liter per second. They have given rate, not rate constant. This is called rate, which is denoted by letter R. Now this is concentration of nitric oxide, concentration of O2 is given. Now from the experiment 1, when the concentration of nitric oxide is 0.30 and oxygen is 0.30, the rate of formation of NO2 is 0.096. 0.096. Similarly, now if you see carefully observe 1 and 2, second observation what they have done, by keeping the concentration of oxygen constant, only nitric oxide is doubled, 0.30 to 0.60. So it is nothing but by keeping oxygen constant, nitric oxide is doubled. Then what happens to rate? Rate increases how many times? 4 times. How many times? 4 times. So by this you can write easily. R is proportional to concentration of NO taken square, because when this is double, this should increase 2 times. Then it is equal to 1. But it is increasing 4 times, because if you multiply 0.096 into 4, you will get it as 0.384. You can check that clearly. So this is nothing but first instance R is proportional to concentration of NO taken twice. Second instance, now if by keeping nitric oxide constant and this is doubled, so observe this reaction. 1 and 3, compare 1 and 3 now, compare 1 and 3. If you compare 1 and 3, what happens? By keeping nitric oxide constant, only oxygen gas is doubled, concentration of oxygen is doubled. Then rate increases how many times? 2 times. This is nothing but how many times? 2 times. So by this, if this is doubled, this is also doubled. So by this you can write rate is also proportional to concentration of O2 only. Now by this we can write rate expression will be R is equal to K into concentration of NO square into concentration of oxygen only. So this is the answer. And the order of reaction will be 2 plus 1, 3. So I hope it is clear. Now let us check the answer. So whenever they are given the tabular form like this, we have to compare 1 and 2, 1 and 3, and 1 and 4, anything, any experiment, so that we will get the perfect data like this you have to. So next, let us check the answer. So as we did, R is equal to rate is equal to K into concentration of NO taken twice, because by keeping oxygen concentration constant, if rate of concentration of NO is doubled, automatically rate increases 4 times. So that's why it is NO square. And here concentration of O2, by since 1 and 3, if you take into consideration, by keeping concentration of NO constant, by doubling the concentration of O2, rate also doubles, 0.096 to 0.192. It is 2 times. So nothing but it is equal. So by this you can say rate is equal to K into concentration of NO2, concentration of NO taken 2 times into O2. Next. So this is one type of questions. Next we are going to discuss other topic in this chapter. So I'm sharing the new one. So next concept in this chapter, molecularity of a reaction. So till now we have done what is order of reaction. So order of reaction is an, what are the basic things about order? Order of reaction is an experimental quantity. It can be zero, negative, fractional, or whole number. Now we'll see about molecularity of a reaction and how to, what is molecularity of a reaction. Simple it is. So let us see now. Molecularity helps in understanding the mechanism of a reaction. It is defined as the number of reacting species. Simple. Number of reacting species, atoms, ions, or molecules taking part in an elementary reaction which collide simultaneously in order to bring about a chemical reaction. So nothing but the number of reacting species involved in a chemical reaction is nothing but molecularity of a reaction. It also may be defined as the number of molecules of the reactants in the elementary step. Elementary step means basic step that are required to form the activated complex, because already you know molecular theory. So activated complex. So what is molecularity? It is also defined as the number of molecules of the reactants in the elementary step that are required to form activated complex. So these reactions are classified as unimolecular. If it has one molecule, we'll say unimolecular. Two molecules, we'll say bimolecular. Three molecules, we'll say trimolecular. And four molecules, we'll say termolecular, depending on whether the number of molecules can be one, two, or three respectively. So one, two, three, four respectively. Next, let us take into consideration unimolecular reactions, means it has only one reactant. The elementary step has only one reactant. These are the reactions in which only one molecule is involved in the formation of activated complex. So example, hydrogen peroxide on electrolysis forms water and oxygen gas. N2O5 on dissociation forms 2NO2 plus half O2. PCl5 on dissociation forms PCl3 plus Cl2. Ammonium nitrate on dissociation forms nitrogen and water. So this is nothing but what? These are all, since only one reactant molecule is involved. Only one reactant molecule is involved. Even we can, in order, we'll say these are all zero order reactions. But in molecularity, we'll say since there are only one molecules, it is nothing but what? It is molecularity is one. So why these are called as zero order? Because for these reactions, as where order is depending on molecularity is only skeletal of the equation, but order is depending on experiment of the reaction. So order for these reactions is equal to, since R is proportional to concentration of H2O2 to the power 0, it is independent of concentration of reactants of N2O5 or H2O2, etc., PCl5 and ammonium nitrate. So we can see these are also called as zero order reaction. That's why I'm telling you again and again, order of a reaction depends on experimental data, whereas molecularity depends only on skeletal equation, that is elementary reaction for complex formation or activated complex. So I hope it is clear. So all these are examples of unimolecular reactions. Bimolecular means two molecules are involved. So these involves simultaneous collision between two reacting species. Simultaneous collision between two reacting species. For example, two molecules of hydrogen iodide on reaction to forms H2 plus I2. So two more numbers also, it is nothing but bimolecular. Our two elements, separate molecules are also bimolecular. So these are all. So if you see this molecularity, the molecularity for this reaction is 2. What is the order for this reaction? These are nothing but what? Pseudo order reaction. This we have discussed in the previous slides. So this is called pseudo first order reaction. So order for this reaction, they'll ask this question only in the exam. So the order for this reaction is order is equal to 1, because rate is proportional to concentration of ester only. Concentration of ester. Whereas molecularity is equal to 2. Molecularity is equal to 2 because two molecules are involved in the reaction. So in the elementary step, two molecules are involved. So that's why molecularity is equal to 2. So that is the difference between order and molecularity. And this is called bimolecular reactions. Bimolecular reactions since two molecules are involved. Next, termolecular. Termolecular means three molecules. Are 2 moles and 1 mole. Are only 1 3 moles. So these involve simultaneous collision between three reacting species. So for example, 2NO plus O2 gives us 2NO2. Molecular reactions are rare since the probability of simultaneous collisions of three molecules with the right energy is very small from a statistical point of view. So these reactions are rare. Rare means they will not occur easily because they have to, all the three molecules should collide with each other with the right energy is very small from a statistical point of view. So for the same reason, reactions of molecularity greater than three are almost unknown. So this is thermolecular, this is tri, but more than three, it is almost not known. So molecularity is always a whole number. It cannot be a fraction or zero because molecularity means reacting species only we have to consider in the elementary step. So it cannot be zero. Very important. Next, the reaction which takes place in single step is known as elementary reaction. The reaction which takes place in single step is known as elementary reaction. And the molecularity of the elementary reaction is the total number of molecules taking part in the reaction. Total number of reactant molecules only, not the total number of molecules. Here we have to do a correction. So this is nothing but total number of reacting molecules, only reacting molecules taking part in the reaction. For an elementary reaction, the molecularity and order are same. For the elementary reaction, the molecularity and order are same. In pseudo unimolecular, it is different. That's all. No example one. For a single step reaction, M plus 2N products, the molecularity is since here one molecule and here two molecules. So the molecularity is nothing but how much? This molecularity is simply it is 3 because 1 plus 2. 2 1 plus 2 becomes 3. So it is clear now. Very simple. So, like this question is basic question. Next, complex reactions, very important. Here it's very important. A complex reaction is the one which takes place in two or more steps. It takes place in how many steps? Two or more steps. Very important. So, like you will see these complex reactions in the formation of tertiary alkyl halides. Tertiary alkyl halides. Reaction of tertiary alkyl halides. So not only this, so many reactions are there. So a complex reaction which takes place in two or more steps. Each step of a complex reaction has a different rate. However, the rate of overall reaction is determined by the rate of slowest step. So the slowest step is always called in a complex reaction is called rate determining step. So for example, if a reaction takes place in three steps, and in all the three steps we have different rates. In all the three steps we have the different rates. Obviously they have different rates. And in that, how to consider the rate determining step? The slowest step is called very important. So the slowest step only we'll consider. It is called as a rate determining step. Each step in a complex reaction has its own molecularity. However, the order is determined for the reaction as a whole and not for each step because order of reaction will write for whole complete reaction, not for each step of the reaction. But molecularity we can write for step. So the molecularity of the rate determining step is usually equal to the order of reaction. So in that case, the molecularity is equal to order of reaction. Let us see how to find order of reaction in these cases. Let us see now. The decomposition of N2O5 takes place in two steps. First step, slowest step, only N2O5 changes to NO2 plus NO3. And second step, what happens? This N2O5 further combines with NO3 and forms NO2 plus O2. So this is fast step. So the overall reaction is 2 N2O5 gives us to 4 NO2 plus O2. This reaction we already know. But in this, the slowest step is NO2 plus NO3. So the first step being the slowest step is a rate determining step. So the order of reaction is equal to the molecularity of this step. So how many molecules it is equal to? One molecule, so two molecules. So hence the order of reaction is one. Because for this, the order of reaction is how many molecules? One molecule. So the order of reaction is equal to the molecularity of this step. So how many molecules here? Only one molecule is involved in the slowest step. On the whole, it is two molecules, but here it is only one. So order of the reaction for this reaction order is one because slowest step is called the rate determining step. So in slowest step, we have only one molecule of N2O5. Second step, we have another molecule of N2O5. But first step, slowest step is called rate determining step. So this word you have to remember. always the slowest step is called the rate determining step, and the order of reaction is equal to the molecularity of this step. So how many molecules are involved in this? Only one molecule. So the molecularity for this only for this reaction is 1. So order is also equal to 1. I hope it is clear. Next. Let us see differences between order and molecularity. So this time from this concept they will give statement-based question. Which of the following is true regarding order of a reaction? Which of the following is incorrect regarding molecularity of a reaction? Like these questions they will ask in the examination competitive exams. So first, order of reaction is the sum of the powers of the reacting species involved in the rate equation. It is equal to the sum of the powers of the reacting species. Whereas molecularity is the number of molecules involved in the collisions in an elementary reaction. So in a basic reaction, elementary reaction, how many reactant molecules are involved? Only number of molecules involved in collisions. Because first molecules involved in collisions means only reactant molecules should collide with each other, then they form product molecules. So order of reaction is determined experimentally, and the concept of molecularity is theoretical in nature, as we already know. Next, order, it is derived from the rate equation, and molecularity, it is derived from mechanism of reaction. It depends upon pressure and temperature, and it is independent of pressure and temperature. Molecularity is independent of pressure and temperature, and order depends upon pressure and temperature because rate is proportional to pressure and temperature of the gas. So order of reaction may be fractional in some cases, but molecularity of the reaction is always whole number. Sixth difference, order of reaction cannot be zero. It can be zero, but molecularity cannot be zero. Order is determined for a reaction as a whole. Order is determined for a reaction as whole with the help of slowest step, but only in terms of reactant present in the reaction. Whereas each step has its own molecularity. In molecularity, it is dependent on the mechanism of the reaction, but order is determined only in the slowest step, mechanism of the reaction also. But molecularity has no dependence on mechanism of the reaction. Each step has its own molecularity. Now example 2. A hypothetical reaction A2 plus B2 gives us 2AB. This type of questions are important for objective. So definitely you'll get one type of question. How to solve this? Let us see. So the follows the mechanism. A2 changes to A plus A fast reaction. Second, this A forming in the first step combines with B2 and forms AB plus B. That is slowest step. Slowest step is called rate determining step. Now A plus B gives us to AB, that is fast. So the order of overall reaction. Overall reaction means we have to consider only slowest step. In slowest step, the number of molecules involved, the molecularity of the what is slowest step is nothing but molecularity. So the molecularity is called order of reaction. So the molecularity means here 1 mole of A and 2 moles of B. So B2, A plus B2. So it is nothing but what? The order of reaction. You can easily guess 3 by 2 because 1 plus 1 by 2. What is this called? 3 by 2 because 1 plus 1 by 2. Because from A2 you'll get it as only A, that is 1 by 2, and this is 1. Why you got 1 plus 1 by 2? Because B2 is considered as 1. And the A2, from A2 only A is formed in this, so it is nothing but 1 by 2. So 1 plus 1 by 2, it becomes 3 by 2. So I hope it is clear. So 3 by 2 is the answer because not all the 4 molecules are involved, only 3 by 2 molecules are involved because this one molecule, this is half molecule. Half molecule because A2 is not completely involved, it is only. What is this slowest step? How to find order for this reaction? Simply nothing but for the statement. Thus, the molecularity of the slowest reaction of the slowest step is called rate determining step. Rate determining step. Since we already discussed about this, so number of molecules involved here, one molecule, and here it is only half molecule because A molecule is not there, A2 is there, but A atom only, so half molecule. So 1 plus 1 by 2 it is equal to 3 by 2. I hope it is clear. So very easy this type of questions. Just see that. Very important this model. Simple is that slowest step is called rate determining step. And in the slowest step, number of molecules involved. Number of molecules involved in the slowest step is called rate of that reaction. Order of that reaction, sorry. Number of molecules involved in the slowest step is called order of that reaction. Let us see one more example. The reaction between 2NO plus Br2 gives rise to 2NOBr follows the mechanism given below. NO plus Br2 gives rise to NOBr2 fast. And second case, NOBr2 so formed in the first reaction combines with NO of the second reaction and forms 2NOBr2. So NOBr2 plus NO, slowest step. So the overall order of the reaction, how many molecules are involved in this slowest step? Two molecules are involved, that is NOBr2. So one is NOBr2 and second one is NO. And in the first step, how many are involved? NO plus Br2. And here it is formed NOBr2. This NOBr2 combines with nitric oxide again and to forms NOBr2, 2NOBr2. So the slowest step is called rate determining step. So I hope you know the answer. So let us see the answer now. And his answer is 3. Why? Because NOBr2 will form from these two. So 1 plus 1, total it is 3. So because 2 here already, and this becomes 1 more. Because this NOBr2 comes from Br2 only, NO plus Br2. So here it is 2 and here it is 1. So total it is equal to 3. Next. Next question. The rate expression for a chemical reaction 2NO2Br gives us 2NO2 plus Br2 is given as rate is equal to K into NO2Br. Rate determining step is NO2Br changes to NO2 plus Br because it is changing only for power 1. So we have to consider only 1, not 2. So NO2Br changes to NO2 plus Br because rate is given for this reaction is only for reactant NO2Br, that too only for one molecule, but here it is given two molecules. So answer is this. I hope it is clear. Next. So this session is very, very important. So rate determining step we have done already. It's very, very important. And I'm closing this session. And next we'll start with new topic. I hope everything is clear for you. Thank you all.